Okay, good morning to all of you. Yeah, so today we are going to discuss the last two concepts in this coding theory. One is introduction to burst error correcting codes and other is introduction to BCH codes, right? Okay, so maybe some portion may be left little bit so that you can cover easily. So I told you that one of the textbook, right? The textbook is coding theory, a first course by Sandling and Zoping Zing, right? So that book may be with you. So, right. So I am also taking material from that textbook only. Okay. So recall that what are cyclic codes, right? In the cyclic codes, so you know there is a generator polynomial, right? So g of x is a generator polynomial. Okay, if it is cyclic code of length with n comma k cyclic code, then what is the degree of the degree of gx?
N minus k.
It is n minus k, right? And what do you know about g of x further? So g of x is monic, right? And we also know that g of x divides x power n minus 1, right? So these are the sum of the things. So entire cyclic code is depends upon the generator polynomial. Generator polynomial further will give generator matrix. Now there is another polynomial that h of x is equal to x power n minus 1 by g of x, right? So this is the parity check polynomial, but generator, so parity check matrix will be constructed differently. You know that we'll write from the backwards coefficient in a reverse direction, right? You know the reason that these two become orthogonal. With that we constructed the parity check matrix, right? Okay, h of x is parity check polynomial. Parity check polynomial. And further what we studied that yeah, so this x power n into h of 1 by x, right? X power n minus k in particular, right? X power k. Why x power k? Because the degree of g of x is n minus k, so the degree of h of x is going to be k. So h of k into x power k into h of 1 by x. So this is the generator polynomial for. Do you recall? This is generator polynomial for which code? So, now this is the matrix we form, right? For the parity check matrix, we'll form with this, right? You remember that? It is called reciprocal polynomial. Remember? This is a reciprocal polynomial. I'm just recalling reciprocal polynomial of h of x, right? Generator polynomial for C perp, right? See, only difference is that h of x is not as it is the parity check generator matrix for C perp. For C perp, the generator polynomial is h power k into h of 1 by x. That is reciprocal polynomial of h of x. Please revise that in the part we discussed in the previous class, so it will be clear. Okay, so and you know that if my x power n minus 1, okay, so I am working in, suppose I am working in, suppose we are working in FQ, right? And then we'll look for, n comma q GCD is equal to 1, right? Because x power n minus 1, so that x power n minus 1 all the roots, so that all the roots of x power n minus 1 are distinct. So that all the roots of x power n minus 1 are distinct. Okay, then x power n minus 1 can be written as some f1 of x into f2 of x into and so on f, so some k of x, right? Fk of x. Then how many generator polynomials can be constructed? Do you recall? Yeah, please.
K.
No, not k, be careful. Generator polynomial is a divisor of x power n minus 1.
So
So I am multiplied that. These are the irreducible factors. Then the number of cyclic codes are, yes, tau function. You remember that. But these are power 111, right? Because they are distinct.
2 power k.
2 power k. Number of cyclic codes are 2 power k. Because there are 2 power k possible generator polynomials. Yeah, I'm just recalling one more time. Yeah, so this is what we studied. So, but how do you decode now, right? Cyclic code is clear now, right? Cyclic code is actually n comma k code. So it is constructed from generator polynomial. Generator polynomial is divides x power n minus 1, right? So there is a one-to-one correspondence between fq power n to fq of x quotienting with x power n minus 1. Right? Yeah, so this part is okay. Now, how we'll do the decoding, right? Much more depth one can go, but I'm just telling the overall picture of decoding, how it goes. Suppose we receive r of x, right? So we receive r of x, then what we do? Okay, then this r of x equal to, so I'm calling this is received polynomial. Meaning is that this is again a vector actually, or quotients wise. Yeah, you know that vector to polynomial to vector and all. Okay, then r of x is equal to c of x plus some e of x. What is c of x?
Code word.
Yeah,
It's a code word.
Yeah, so some error will be there, right? This is a code polynomial, code word, and this is error, right? Correct, this is error. But now what we do? Okay, so what are code words in cyclic code?
Multiples of gx.
Thank you very much. Yes, okay, now that you already remember. Okay, thanks that part. Now the code words are actually some I of x into I am writing information, right? So I of x into g of x, such that degree of I of x is less than or equal to n minus k plus 1, n minus k minus 1, because we are quotienting with x power n minus 1, right? See, we are quotienting with x power n minus 1. So once you've done that, then the polynomial degree is at most n minus 1, but degree of g of x is n minus k. So what is that I can multiply? I of x degree is how much? Minus 1, right? So what is this? Yeah, okay, you remember that. Okay, so this is the thing. Yeah, right. Okay, so actually so c of x belong to c implies that g of x divides c of x. Wonderful, this is what I am looking for. Yeah, good. Now so therefore what I will do, so if so then r of x, now syndrome, you know, syndrome is a by using syndrome we can find or detect, right? So syndrome vector s of x is equal to r of x modulo g of x. to check whether it is a given code is a correct or not, I will do modulo gx, right? So, but it is equal to c of x plus e of x, okay, mod gx, right? Mod gx, right? So this implies that, oh, some problem came, sorry. Yeah, now this is equal to s of x equal to c of x into e of x plus g of x, which is equal to e of x modulo g of x, right? Okay, so that means actually, what is s of x actually? This is a remainder, right? So s of x is the remainder after dividing with dividing with g of x. Is there any? Are there any questions? Yes, right? Yeah. So are there any questions? Okay. Now we are going to the, so it is simpler. We can much better we can do actually syndrome vectors. Okay, now I'm going to the my topic of today's topic. So that is burst error correcting codes. Okay, burst error correcting codes. Okay, let me explain that first. What is burst error correcting code? Right. Yeah. So first I will define something. Yeah. So concentrate. So why burst errors? Actually, generally, usually, till now the coding theory till now we done, they are going to correct random errors. We do not know how error comes, where comes. So we are not at all care about. But usually errors usually comes in the very short duration, right? Even in the disk storage पे एक जगह पे होगा सारी की सारी errors, right? So those are called burst. Only at locally errors are happened. Then cyclic codes are very useful to correct them. Yeah, so that is the idea. Okay, so let me explain what is burst decoding. So first let me give you the definition, right, so that it will be easy for you. Okay, so yeah, please ask me whenever you have a doubt. Okay, so definition, say a burst of length L greater than 1, okay, is a binary vector. Oh, sorry, I am now talking about only safe side. I am just confining to binary. Okay, na? Till now I am talking about FQ, but yeah. So make it easy. You can extend it to any field. Okay. A burst of length L greater than 1 is a binary vector. Whose non-zero components confined to L cyclically consecutive positions. With the first and last position, with first and last positions being non-zero. So in the binary being non-zero means, what is the meaning? First and last position being non-zero. Yeah,
Both are one.
both are one. Yeah, very good. Thanks. Yeah. Okay, so I'll explain with one example so that it will be clear. Okay, so look at this. So 0011, right? 01. Okay, then followed by 4 zeros. Okay, so can you tell me what is the burst and what is the length? Burst of length. See, look at this part. Okay, so look at this portion. Yeah, it is not that visible.
So 4.
Uh,
4.
yes, it is 4. Burst of length 4. Okay, so because this is the first position, this is the last position. These two are non-zero, remaining entire thing. This is the burst of length 4. Wonderful. Okay, one more example so that it will be clear to you. Correct. So one more example I'll give you. So tell me here, but be careful that there is a cyclic shift also. I will to make that part, I will give one more example. So for example, 0, 1. Okay. So 1, 2, 3, 4, 5. 1 minute. Yeah, okay, whatever it may be. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 1, 0, 0. Okay, let us I take something like this. Okay, then is a burst of, can somebody tell me? Yeah. So it is not burst of this much length, okay? Be careful. I can shift cyclically, right? Are you following? If this is a word, then you know that so I can take 0 to this side, right? So 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 0. This is also a cyclic code, right? It is also another code word, right? So now can you predict? Like that I can make 2 more rounds. Yeah. Now can you predict?
5.
5, correct. So it's a burst of cyclic of length 5, right? Of length 5, right? So that is actually so that is 1, 0, 0, 0, 1. So this is the thing. So if you cyclically shift this portion and this portion, right? So I'm going to get like this. So it is a length of 5. Yeah, good. Thanks.
But, so why is it not the other one?
Which one? This one?
The
No,
here.
no. No, no. See, I will take the smallest one. So that is what a burst of length n. I'll take the least one. That is not given here. Components confined to L cyclically consecutive positions. Cyclically consecutive positions. Consecutive is also missing na, here. Here, here it is coming. It is like consecutively, but I will take the least actually. Yeah, that is not given in the definition, but that is the we'll try to take the least one. Is it okay?
I did not understand what you mean by L cyclically consecutive positions.
Cyclically conjugative means this is so after that again it is cyclic shift. Uh, so so consecutive means what? For example, 0, 1, 0 is consecutive, 0, 1, 0, 0 is consecutive, like that, right? So in fact, 1, 0, 0 last 3 and 0, 1 is also considered as a consecutive only, but it is cyclically. Okay, because I have this word, then I have this word also. I have another word also, right? So in one of them, the least thing is considered as that part. Yeah, but they not define that much rigorously. What is that I want to say to you is that you take the cyclic shifts and then the smallest length you take. Is it now okay? That part is fine.
Okay, sir.
Okay, so now the next thing is that so so now I am telling you one thing. So definition again. So definition. So definition. A code. A code means a capital C, correct? Collection of code words. A code is called L burst, L dash burst burst error, okay, correcting code, burst error correcting code. Okay, if it can correct all, it can correct all burst errors of length L. Of course, less also. So that is what? That is error patterns. That is error patterns of length Oh, better I'll write one more thing also. Error patterns that are bursts of patterns that are bursts of length L or less. See, what is error pattern? The error pattern is that E of X. This is called error pattern, right? C of X is called, this is called error pattern, right? My error pattern is like a burst error. Then if it is less than L, then I can correct actually, not only detect. Okay, so let me explain those things in a while, right? So let me explain those things. Yeah, so look at this part. Okay, so for example, okay, let us take some small example. Okay, my binary word is I'm not telling it is a code word. Okay, only word. Okay, some word W is equal to 0, 0, 1, 0, 0, 0, 1, right? 0, 0, 0. Let us say like this. Then you know that this is the burst, right? So burst of length 5, right? Burst of length 5. Then what is a polynomial corresponding to this? Can you suggest? So you write like this, na? A0 plus A1 is like that. Can you convert into a polynomial and say? Right. Hello?
X raised to 4 plus 1.
Yes, please.
X raised to 4 plus 1.
No. See, what is a polynomial corresponding to this?
X square plus X power 4.
X square. Yeah. So it is actually 0 plus 0x plus 0x square plus 0x cube plus x power 4. Correct. Yeah. We are converting the this word into polynomial, right? We are converting into polynomial. So like that, can you say about this polynomial corresponding to this?
X square plus X power 6.
So 0 into 1 plus 0 into x plus 1 into x square plus 0 into x cube, 0 into x power 4, 0 into x power 5, yeah, x power 6. Yeah. But how do you write this now? It is equal to x square into 1 plus x power 4, right? So, but what do you know about g of x? G of x divides x power n minus 1. Do you remember that? Yeah. Yes. And what is the GCD of now? So you can easily see that the GCD of, let us call this polynomial as W of x, right? This corresponds to this W. Okay. So what is the GCD of G of x comma W of x? Can you say something? It is simply GCD of x power 4 minus 1 comma G of x. Do you agree with this? Hello?
Yes, sir.
Yeah, right. Because x square GCD of x square comma g of x is equal to 1. X square, there is no common factors for x square and g of x, correct? So I only consider only this portion, right? So that is x power 4 plus 1 or 4 minus 1 is same. And again, suppose that uh, suppose degree of g of x is greater than 4. Yeah, degree of g of x is greater than 4, right? Can it be a code word? Even GCD also not required. Forget about this. Okay, so just I wrote what is GCD, but yeah, so it is sufficient to consider only this portion I want to tell you. But uh, yes, okay. For example, my entire polynomial degree of, first I'm coming to this, degree of W of x is less than degree of G of x. Okay, can G of x divides Wx?
No,
No,
sir.
right? No, no. Degree of Wx is less than degree of Gx. How would G of x divide Wx? Then, if this is my error vector E of x, right? So then there is remainder comes as it is, right? When I divide it by G of x, correct? So for example, this is my S of x is equal to, you remember that, right? C of x plus some E of x, right? But E of x degree, if this degree is less than degree of gx, then my remainder becomes this is E of x mod gx only. There is no change. It is further not modified. So in general, it can be modified to, after doing modulo gx, we'll get something else. But if its degree is less than gx, then it comes as it is. It is a remainder, right? So that means that now as it is remainder comes, then but it is not a zero polynomial. Are you okay? Yeah. So then what is going to happen? Can I detect the error? Tell me, can I detect the error? Or not following? When I can detect the error? When I cannot detect, when I can detect. What happens if S of x equal to 0 polynomial? Syndrome is 0, then what happens? Are you not following? Okay, what is syndrome?
Is a code word.
So syndrome is actually received word ka I'm looking syndrome I'm calculating. That is Ex plus Ex. So it is like this. If Ex is 0 polynomial, then I will not detect any error at all. Correcting a chodo. You cannot anyhow correct. Even you cannot detect. Okay. And further, my E of x degree is less than Gx, right? It is irrespective of burst length and all. It's very easy from here itself. But I'm telling that in the burst code that the Wx looks very nice polynomial. It is some x power k. It's finally it is like x power k minus 1 something. Remaining part I don't care. Yeah, even that is not divisible, then I'm getting. So very easily you can check things. Yeah, error is there. You can easily check. Right. Yeah. So what? Okay, I'll come to that. So now, so we can detect whenever even this 4 is less than degree of g of x. Also, g of x cannot divide. Okay, it cannot be 1. It cannot be g of x. It cannot be g of x, right? So I cannot detect when this polynomial is divisible by g of x, but the degree of this part already x square part. This is not even this portion is more, right? Some portion will be there, but remaining part, if it is divisible by g of x, then there is a problem, right? But that itself is degree less than 4, then I can't. Yeah, and we'll go much further. Yeah. So is it okay? I'm getting some more picture actually. My burst error, if the error is burst error, then I'm getting more picture than actual errors. Yeah. Okay. Okay. So now I'm coming to small theorem here to results I'll state. Proofs are very straightforward, but even then, yeah, let me state this. Yeah, but before that, do you have any questions to ask? Okay. So a linear code C is an L burst error correcting code burst error correcting code if and only if all the burst errors of length L. Okay. So remember that here I am telling correcting. Yeah. Of all the burst errors of length L or less. Yeah, sorry. Now suddenly this is changed. Yeah, so all bursts of length L or less. Okay. Lie in distinct cosets of C. Is a statement clear first? See, I received a code word, right? R of x. So R of x equal to C of x plus E of x. Now my E of x is of length L, right? Or less. Then I will construct the syndrome, right? If they are lie in the different cosets of C, then I am done. Why? If they are in different cosets, then I can easily. So when I cannot correct if both are in the same, both errors are in the same coset. Are you following that part? So remember that we constructed standard array, syndrome table and all. You remember that?
Yes, sir.
See, if both are in the same coset, then what happens? Both will correct to the same code, right? Then I cannot detect. Na? I am doing wrong, right? So both different errors, but I am giving to the same code, correct? Because that what happens is that so I can correct exactly to the correct code word provided the burst errors of length L or less lie in the distinct cosets of C. If they are distinct cosets, there is not a problem, right? For example, proof is also nothing actually. If all the burst errors of length L are less in the distinct cosets, then each burst error is determined by its syndrome, right? Then error can be corrected through its syndrome. Done. That is the first part. Second part is that, so for example, B1 and B2 of length L are less in the same coset. Then see, B1 minus B2 is a code word. So then there is a problem. B1, B2 both are corrected to, can be decoded to 0 code or C code. Different, right? Yeah, this is one of the theorem. And other theorem, first let me state, then we'll try to see the proofs, okay? So another theorem related to this burst coding is that, and actually this is actually corollary to this actually, this simple. Then we'll see the proofs of all these things if nothing is clear to you, yeah? So, but corollary is most important. Let C be an NK code, NK linear code. Yeah, when we write like this, after automatically it is linear, but NK linear code, okay, which is also, which is first error correcting code. Okay, L dash, L burst error correcting code. Then what is going to happen? Okay. First one is that no non-zero burst no non-zero burst of length 2L or less can be a code word. Okay. Second one is that so n minus k is less than or equal to 2L. Okay. This bound is called rigor bound. Okay. Yeah. See, I give the proofs here, but I want to show somewhere. Okay. I'm stop sharing and I'll show something. I'll share something else. Okay. So that it will be clear. Okay. So this is Wikipedia. Of course, no need to follow Wikipedia, but I'm just telling you that here also you can read in future if you have problems. So here they're given very nicely. Means I'm checking at different places where material can be collected. But I luckily saw that Wikipedia gave very nicely about burst error correcting codes. Just I want to convey that to you. Not that even a textbook which I shared also fine. See, so are you able to see this? Mehak, Wikipedia site, are you able to see?
Yes, sir.
Yeah, okay. See, so burst here they also gave burst error much more pictures and everything given, right? Yeah. So cyclic of burst length also they gave. Okay. So now, so burst description also they gave, right? So look at here. So this is the theorem I'm talking about. Every cyclic code with generator polynomial of degree R can detect all bursts of length less than or equal to R, right? That is what I'm talking about, right? So when it is a burst error, then my directly later it is x power I into b of x. You remember that I'm talking about after taking that whatever common, then degree of b of x is less than R. Therefore, b of x is not divisible by g of x, right? So that is a one thing. It's very simple direct consequence. Now this another result, distinct cosets. Here proof is also given. Okay. So linear code C of length of L burst correcting code if and only if all bursts of length less than or equal to L lie in distinct cosets of C. So proof is given very nicely here. Yeah. And burst error coding classification. So let C be a linear L burst correcting code, then no non-zero burst of length less than or equal to 2L can be code word. The proof is given here. Very simple, straightforward. Yeah. For example, what is that proof goes like this? You take it is a burst, right? So burst means starting with one, ending with one will come, right? Length 2L. So length 2L means now what we can say about U and V, right? So U and V are words of length less than or equal to L minus 1, right? So U less than or equal to L minus 1, V less than or equal to L minus 1. So they are less than L minus 1, L minus 1, total together 1 together मिलाकर हमको होगा 2L length होगा at most, right? Yeah. So now what they done, they took the word these two, so they took this word, right? 0 1 U 0 0 0, correct? Okay. And so this proved by contradiction. This proved by a contradiction, right? Suppose it is a code word. Which one? If this is a code word, prove by contradiction, I remember. Suppose this 0 1 U V 1 0 is a code word, right? Then what happens? Yes. Then the words 0 1 U 0 0 0 and C minus W is this are two bursts of length less than or equal to L, right? Are you okay? Are they bursts or not?
Yes, sir.
Yeah. So they are bursts of length also less than or equal to L, because U is word of length less than or equal to L minus 1, right? So they are bursts of length less than or equal to L. For binary codes, so but they belong to distinct cosets, right? So therefore, no burst of length less than it can be a code word. Yeah, proofs are very straightforward, not complicated. But I'm not saying that I'm following Wikipedia and all. But sometimes it's okay to tell the source where burst error correcting codes given very nicely. So this is one place I want to say. Is it okay now? Is it fine with you regarding the burst error correcting codes? In future, if time permits, I'll give the more examples. So can I proceed to the next concept? Or you have any
Yes,
question?
sir.
Actually, here more information is given, but yeah. So some examples also given here, but there are more concepts. So fire code and very many areas of this will be there, but we need just elementary burst error correcting codes. Okay. So final conclusion is that the conclusion is that so cyclic codes are better for burst error correcting codes को tackle करने के लिए. Yeah. Yes. Yeah. So then I will take a small break now, and we'll meet again to discuss. Right. So this will be useful when provided you clear with little bit of that cyclotomic cosets. Okay, anyhow. So let me start. Let alpha be a primitive element of fq power m. So m alpha I of x is a minimal polynomial of alpha power I with respect to fq. Is it clear? You remember this? Minimal polynomials you remember, right? Yeah. If alpha is a primitive element means what?
Generator of FQM minus
0. Yeah, generator polynomial, generator. So this is a finite field and alpha is a generator. Since we know that fq power m minus 0 is a finite field, so alpha is a generator. Then we know that all the elements in fq power m now becomes 0, 1, alpha, alpha square up to alpha power q power m minus 2, right? So then each alpha you take, then you know that alpha power p, alpha power 2p and all, so something, right? You remember that p square, alpha power p square and all, they have the same minimal polynomial. Like that we constructed the cyclotomic cosets. Yeah, so before going to this, next time, please go through that cyclotomic cosets one more time, how we constructed the minimal polynomial, how we factored x power n minus 1 over fq power m. Yeah, that will helpful. Yeah, okay. So m alpha power I is a minimal polynomial. Then the primitive BCH code. So there is we cannot, no need to take the primitive. So what is the difference between primitive and non-primitive? I will also explain. See, this is the one of the crucial point. So for all different, but nothing actually, not much difference. See, we are looking for, you remember that we are looking for x power n minus 1 in cyclic codes, right? In cyclic codes. So cyclic code of length L related to x power n minus 1, right? But what is n here? We need that n comma q GCD should be 1. Why? We need that because we are working in fq of x. We are working in fq of x. So if GCD is not 1, then there is a problem we'll face because it may have a repeated roots, right? So because that now n comma q GCD 1. But when we are working in fq power m, right? So do you know, what do you know about fq power m? This is not the first time, but again I'm recalling. It is fitting field for which polynomial? Fq power
x
m.
power q power m minus x.
Yeah, x power q power m minus x. And you know that it
Over
is equal to
FPX.
Over fqx. Very good. Over fqx. Wonderful. Yes. Yeah. And further, we know that it is a product of irreducible polynomials, right? Product of some irreducible polynomials. We know about their degrees also. You remember that? They are going to divide m. Okay. That follows from the fact that subfields. You remember how I explained it at that time? There is a concept called subfield. Subfield dimension divides the dimension of that original degree, right? So based on that, we'll get that all the polynomials here, the degrees are degrees divides m, correct? Yeah. So now, now I take x outside, right? When I take x outside, what happens? You know, when I take x outside, what happens? It is equal to x times x power q power m minus 1, right? Yeah. Now, when n divide this, so you know that another thing we discussed, x power n minus 1 divides x power m minus 1 if and only if. Do you remember that?
N divides M.
N divides m, right? This also very useful to understand these BCH codes and all. But actually BCH codes is nothing. BCH codes is cyclic codes only. Only difference is in the BCH codes is that how do you compute the g of x? Yeah, g of x, it is a divisor of x power n minus 1. But we will choose the g of x in such a way that, so my distance, whatever the distance you give me, I can construct a code whose distance is greater than or equal to d. That is the more beautiful and why this become famous. So generally we do not know what is the distance of the code a priori, right? But now it is possible for us to construct a code whose distance is greater than or equal to d. That is what Bose, Chaudhary, and Ackingham so came up to. That's why cyclic code also become famous, and so that is the thing. Yeah, but all these things are depend upon this. I'm sorry for that, but I explained these things earlier in the finite fields way. So that's why we need to discuss finite fields, right? What is the reason for introducing finite fields to you? Cyclic codes are very much depends upon the factorization of this x power q power m minus x. These factors also comes from. So how many factors will be there? Do you remember? Is equal to what? Number of factors equal to. For example, this is how many factors will be there for x power q power m minus 1 minus 1?
Number of cyclotomic cosets.
Oh, thank you very much. That is the thing. So yeah, okay, good. That is related to the number of cyclotomic cosets. Each cyclotomic coset will give one irreducible polynomial, right? But now, when I take x power n minus 1, right, x power n minus 1, if it is not equal to, see, n is a divisor. In general, for BCH codes, n need not be equal to q power m minus 1. If n equal to q power m minus 1, then GCD of n comma q power m minus 1 is 1. So I'm happy. But so that much is not required actually. N divides q power m minus 1 is also works. Okay. So you take any n which is GCD with q is 1, then I can take the some power where n divides is q power m minus 1. That can be proved easily. So based on that, it comes actually, right? But that again comes from, if you want more specifically, then Dirichlet's theorem, right? So 1 comma q power m GCD is 1. So in the Dirichlet theorem says that you take any arithmetic progression, it has infinite number of primes and all. From that you can easily get it. Yeah. Okay. But primitive BCH code means my n is equal to q power m minus 1. I want to tell you that n need not be q power m minus 1 in general. For primitive BCH codes, n equal to q power m minus 1, right? In that case, the number of cyclotomic cosets, so of this one, q power m will work. So my n is equal to q power m minus 1, right? If you remove that n only divides q power m minus 1, then I simply will call BCH code. So the BCH code with n equal to q power minus 1 is called primitive. Yeah. Any doubts? First, primitive, non-primitive. I hope there is no doubts related to primitive, non-primitive. Right? Okay. Now again come back and define properly. Right? So let alpha be a primitive element of fq power n, right? And this m alpha power I is a minimal polynomial of alpha power I with respect to fq. A primitive BCH code over fq of length n equal to q power m minus 1 with designated distance delta is a Q-ray, means alphabet is fq. That is called Q-ray cyclic code generated by my g of x is this LCM of m alpha power a of x, m alpha power a plus 1 of x, m alpha power delta minus 2 of x. Is it okay? Is this clear? G of x is constructed by the minimal polynomial. So you know that each m alpha power a of x is a divisor of which polynomial? This divides what? It divides x power n minus.
GX.
Yeah, it divides x power n minus 1, right? Huh?
It divides GX.
Gx also it divides because it's LCM, so that quite obvious. But what are these? Okay, see, each minimal polynomial actually divides, right? It is actually x power q power m minus x equal to product of some polynomials, right? We are factoring it actually. The factors are corresponding to the cyclotomic cosets, as you rightly pointed out. One of them is x, of course. Usko छोड़ने के बाद, that is x power m q power m minus 1 ka, right? And these are exactly the minimal polynomials, right? Right. So they are actually divisors of x power n minus 1, correct? That is very much needed for me, correct? G of x should be a factor of x power n minus 1. That is needed now for cyclic code. But now we are taking a special form, special generator polynomials. They are LCM of these things. That is the definition of the BCH code. Yeah. So for some integer a, so a alpha power a से शुरू होके a plus 1 a plus 2 up to a plus delta minus 2 तक जाएगा. Okay. Furthermore, if my a equal to 1, what is this? If a equal to 1, where from where to where I will go? Can somebody help me? Then in that case, what is my g of x? G of x is LCM of, yeah, please. A equal to 1, right? M of alpha x, comma, m of alpha square of x, right? Up to what extent I'll go? M of alpha power. Can help me here?
Delta minus 1.
Delta?
Minus 1.
Yes, delta minus 1 of x. Okay. So, but you know that, for example, if I work in binary, what is the minimal polynomial of, what about these two polynomials? Do you know something?
They are co-prime.
They are co-prime. Be careful. See, you know, C1 is a cyclotomic coset containing 1. So what it contains, right? 1 into 2, 1 into
For
2
two,
square.
it will, yeah. For two, it is not. For other
Ah,
primes, it is.
yeah, for 2 it is there, both are same. I am asking for binary. Binary
Yeah,
pay
for binary, they will be same. For other primes, they will be co-prime.
Yeah. So my point to inform you is that sometimes they may be equal. Okay, that's why we are taking LCM. Yeah. But if they are distinct, you are correct. Their GCD is exactly 1 because they are irreducible factors, right? So that is the beauty of this BCH codes. Okay, you will take. So let me clear now. This n is simply divisor not equal to q power m minus 1, just BCH code. That BCH code is called primitive if n equal to q power m minus 1. Now, if my a is also 1 here in the definition, then it is called narrow sense. But don't worry, all these things. These are just names only. Yeah. So let me explain with one example. Let alpha equal to alpha belong to f8 be a root of this polynomial, right? And you know that this is exactly, if you want, you can see that x power 8 minus x equal to what? Do you remember? X times
X minus 1.
very good. X minus 1 into x minus 1 is a minimal polynomial for which alpha power something?
X
It is
square minus 1.
no. What is that I want to say? M alpha power something, right? Is equal to x minus 1. Can you say that?
What?
Here alpha power I, right?
7.
7 is okay, but it is 0. 7 or 0, correct? What is the minimal polynomial of alpha power 0? What is alpha power 0? 1. What is the minimal polynomial of 1? X minus 1 only. What is the smallest polynomial for which 1 is a root? Right? This is m alpha power 0. Okay. What are other polynomials which are roots of this polynomial? So that is 1 plus x cube, correct? Other polynomial 1 plus x square plus x cube. Do you remember this? These are irreducible. Why they are irreducible? 0 is not a root, 1 is not a root. Here also 0 is not a root, 1 is not a root. So x power 8 minus x I can divide like this. Now, now what are the cyclotomic cosets now? One cyclotomic coset is 1. Other cyclotomic coset is 0. Sorry, 0. Other cyclotomic coset is 1 comma 2 comma. Do you remember that? 1 comma 2 comma 4. Okay, this is one cyclotomic coset. Next, corresponding to 3. So 3 into 2 6. 3 into 2 square, 3 into 4. 3 into 4 is 12. 12 means modulo 8. Sorry, something is missing. I have to take 7, right? I'm working on 7. So yeah. So 12 5, right? Yeah. So 3 6 5. 3 comma 5 comma 6. Are you okay? I'm doing modulo 7 is okay. Hello.
Yes, sir.
Why doing 7? It is not. I remove x. Okay. While working, then I will not. I will work in x
But we
power.
have already taken 0, so that is the same as 7.
Not only that, actually. See, so forget about x actually. So we are only concentrating on x power 7 minus 1. This is equal to x into x power 7 minus 1, right? So this is the modulo I take generally, right? 1, 2, 2 into 1 into 1 into 2 power 0 modulo 7, 1 into 2 modulo 7, 1 into 4 modulo 7, 1 into 8 modulo 7. What is 1 into 8 modulo 7? Again 1. It is repeating. So 3 into modulo 7, 3 into 2 modulo 7, 3 into 3 modulo 7, right? So we'll get this. So now we'll get all of them. 0, 1, 2, 4 and all. Okay. Corresponding to this, x power 7 minus 1 factors. This is corresponding to 0. This is corresponding to, this is a minimal polynomial for which roots now? It is a minimal polynomial for alpha. It is also minimal polynomial for alpha square. It is also minimal polynomial for alpha power 4. Okay. So actually this x power, you remember that this is actually equal to x minus x into x minus 1 into x minus alpha into x minus alpha square into x minus alpha cube into, like that will go up to x minus alpha power 6. But x minus alpha into x minus alpha square into x minus alpha power 4, they're all roots of the single polynomial, that is this guy. Its roots are alpha, alpha square, alpha power 4. Its roots are alpha cube, alpha power 5, alpha power 6. Any doubts further? Please let me know. Okay. Yeah. So alpha is is a root of this polynomial. Then it is a primitive element of F48. Luckily, see, it is not always that you take whatever alpha, that is a primitive root. Okay. So I'll give one example. So here I am writing. Okay. For example, you take F9. F9 means F3 square, right? So is it, what about x square plus 1 is irreducible in F3 or not?
It's getting blocked. Can't see
Oh,
that.
it is blocked. No?
Now it's fine.
Okay. So see, x square plus 1 is irreducible in F3 of x. Do you remember?
Yes, sir.
Yeah. So now F9 is equal to what? F3 of x quotienting with x square plus 1.
Yes, sir.
Now, but what is the root of this one? So let us say alpha is a root. Is it a primitive element?
No, sir.
No. Okay, be careful, try to understand that. Okay, so what is that I want to say that so actually f9 is equal to so I'm just giving some caution. Okay, why we are writing like that? This is x cube x square plus 1, right? Sorry for this one. Yeah, so it is actually f9 is actually this. So but the root of x square plus 1 is no longer primitive element. Okay, in general it not happen, but here it is happening. That's what I want to convey. Then it is a primitive element of f8. So the polynomials m alpha of x, m alpha square of x both are equal to 1 plus x cube. So I told recall cyclotomic cosets. Then what is LCM of m alpha x, m alpha square of x? It is simply 1 plus x cube gx. Now the cyclic code with gx is an arrow sense binary BCH code of length 7. Okay, so narrow sense. Okay, also primitive also, right? Narrow sense binary BCH, narrow sense primitive also. Yeah, primitive. Why narrow sense? Do you remember why narrow sense?
I don't know what narrow sense means.
Yeah, we are starting from 1 here, right? 1 and so you are going consecutively, you know that. Yeah, all a plus 1 up to a plus delta minus 2. But now my a equal to 1. So when a equal to 1, it is narrow sense, right?
Okay.
So yeah, so 1 and 2 I stopped here, and this is g of x. Now we'll go to 7 comma 4 code. Why will get 7 comma 4 code? Because the degree of g of x is 3, that is n minus k. So I'll get 7 comma 4 code. This way I gave in my previous slides also. So you can in the lecture notes. So actually it is a 743 Hamming code. Okay, now suppose that I take now, right, alpha power 0. Now I am taking alpha power 0, alpha power 1 and alpha square. Now it is not narrow sense. Why it is not narrow sense? Yeah, I'm starting with 0, not at 1. Okay, but for 0, what is the polynomial, minimal polynomial? Alpha power 0, 1 minus x or x minus 1, right, into this related to this. Now what is the degree of this g of x now? Yes, please. Degree of g of x is 4. Now
4.
what is the code? Cyclic code I'll get 7 comma 3 cyclic code. Actually it is a dual. Actually this is my dual code of that earlier code, this one. Okay, you can check that. Yeah, so I explained Hamming codes earlier, and this particular code is given in the previous lecture note. So I hope it is not a problem to you. So the parameters of BCH codes are, now I'm coming to parameter for primitive, right? If it is not primitive, it is a divisor of q power m minus 1. For primitive, it is q power m minus 1. Dimension of the q array BCH code of length q power m minus 1 generated by, this is LCM of this, right? Generator polynomial comes from here, right? But what is the degree of this polynomial, right? Degree I will take the union, right? Cosets ka union leta hu, right? So then I take the cardinality of the union of these cosets, right? Degree is equal to products, right? So where C is the cyclotomic coset of Q modulo Q power m minus 1 containing I, right? So the degree of g of x is n minus k. Then so this n minus k coming from the cardinality of this part. Is it okay or not okay?
Yes, sir. Okay.
Because see, sometimes there may repetitions come. Okay, so that's why I'm taking union, so repetition gets cancelled. Then whatever the remaining disjoint will come, right? That cardinality is the degree of g of x, right? Beautiful, actually. So whatever comes, I don't know, depending upon the alphas and where you are working, it depends on many parameters. But once I have this cardinality, then the degree of g of x is n minus k, exactly. If it's n minus k, then it is a cyclic code. Now distance is at least q power m minus 1 minus m times delta minus 1, where delta is the designated distance. Okay, designated distance is in the definition, it is given. So I wrote in a yellow color also, right, in the definition. So what is this delta? Delta is I'll go up to a plus delta minus 2. That is the delta. Wherever I go, that is called designated distance. Now, once you start with BCH code means you are starting with the delta. Then the distance now beautifully that q power m minus 1 time minus m times delta minus 1. This is the distance. Okay, so to explain you, I will state one result. I'll prove that. With that, I will stop today. Yeah, so that is a beautiful result, and it will tell you that why designated distance is at least delta, something like that. It will come. Okay. Yeah, proof is very nice. Those who are there in the previous class, Van der Monde matrix and all, why I introduced everything now comes into picture. Yeah. So proof becomes very, very interesting. With that also I will stop. This is the last result I want to tell you. And with this, I'll also close my coding theory part of this course. Yeah. Okay. So let me state the theorem. Okay. Theorem says that a BCH code with designated distance, design, and some people call designated, some people call design distance. Yeah. A BSH code with design distance delta has minimum distance at least delta. Okay, you will understand this. Don't worry. A very simple, nice proof actually. Okay. Okay. So let me recall things one after the another. What is the minimum distance of a code? You remember, right? Recall. So actually proof will not be written like that, but yeah, I'm writing here. Recall what is minimum distance, right? Okay. Do you remember this? Ours is a linear code. Yeah.
Minimum weight.
Minimum weight. Yes, thanks. It is minimum weight, right? Yeah, I'm writing just minimum weight. Minimum weight of non-zero code word, right? Minimum weight of non-zero code word, right? And that is equal to what? Now, when we are working in the cyclic codes, when we work in cyclic codes, okay, so let us, I will not call this as a proof. So discussion before that. So first a little discussion, then go into the proof. Yeah. So when we work in cyclic codes, okay. So you know that code words are polynomials divisible by g of x, right? So and so what is weight of some polynomial? Weight of fx equal to what? Can you say something?
F of 1.
No, I take a
F
polynomial.
of
No, be careful. Do not before telling. So polynomial and associated with the code word, right? So there is a one-to-one correspondence. Now, for example, a n minus 1. Okay, what is the polynomial corresponding to this?
A0 plus
Yeah. So
A1x.
a1 x plus and so on plus an minus 1 x power n minus 1. Correct. Now, so what is the weight of a vector? Okay, what is the weight of the polynomial? So think this as this, okay, or polynomial, whatever. So can you tell me now weight in terms of something?
F of 1.
Not f of 1. Okay, f of 1 when you are working in binary, correct?
Yes, sir.
Yeah, very good. So very nice idea. Is equal to f of 1 when we are working in binary. Otherwise what? Yeah, very good. Actually, this is very nice. So how many of you followed other than Amya? Since the answer is given by Amya, so obviously you understood because he is the person gave the answer. What is f of 1 actually? If I take a polynomial, if I substitute 1, what I am going to get? Suresh?
Sum of the coefficients.
Sum of the coefficients. If it is a binary, what is f of 1? I'm working in binary, right? That means AIs are 0 or 1. Then what is f of 1 will give you in this? Putting f of 1 here and what is that f of 1 will give here? He told very nicely. F of 1. Yeah. F of 1 will give the number of ones, right?
Yes, sir.
So number of ones, that is the weight of the code word, weight of the
Yes, sir.
word actually. Yeah. So weight of the word is that, right? But if I work any field, then what is generally weight of fx? Weight of fx is simply that number of
Non-zero.
non-zero coefficients. But luckily, when you are in binary, that comes directly from f1, number of non-zero coefficients. But your idea giving me some more questions actually to me. Okay, in future I will look into that. Is there a general way for other finite fields also I can come up like this? Suddenly you told f of 1, but it is very nice answer actually. Yeah. Anyhow, I will look into that in future. Weight of f of x equal to number of non-zero coefficients. Good. Okay. So number of non-zero coefficients. That's why I can define support of fx, right? Support of what is support of fx? All the coefficients where they are not equal to 0, right? Support of fx equal to so the set ai, so that ai is not equal to 0. Are you okay? Is it okay? Support is fine. Yeah. So sup of f, is it okay? So
Yes, sir.
now weight of f equal to what? Cardinality of sup of f. Okay. 1 minute. Just give me 1 minute. Yeah. Okay. So weight of f equal to support of f. Okay. I hope this much is okay. No doubts. Okay. Thanks. Now let me start the proof then. Right. Proof. Now come back to the question. What is the question? Statement is very simple. A BCH code with minimum design distance delta has a minimum distance, at least delta. Right. Okay. Now come back. Very nice actually. This is let alpha be the primitive element. Let alpha be done, be a, right? Primitive elements are not unique. Alpha be a primitive element. Primitive element of f cube power m. Okay. So are you here? All of you are okay?
Yes.
Yeah. Okay. Thanks. Let C be a BCH code. Let C be a BCH code generated by right. So you know that the BCH code generated by GX, right? So it is equal to what? You know that it is LCM of G sorry, M alpha. So designated distance delta I told, right? But it is generated by, so somebody tell me where it starts. Some A, right? MA of X. Next one is what? M. Yeah, just tell me one, just repeat. M alpha power
A plus 1.
A plus 1, right? Alpha power A plus 1 of X, correct? And last one is M alpha power A plus delta minus 2 of X. यहाँ तक जाएंगे, right? Yeah, okay. LCM of these things, right? Okay. Now, so okay, this is the beauty. Now, suppose minimum distance d of C, okay, is less than delta. Okay, I'm proving by contradiction, right? Recall the proof again. So statement again. So minimum distance is at least delta I want to show. That means it is less greater than or equal to delta, but I am assuming that the distance is less than delta, right? Is it okay? Clear? What is that I'm doing? I'm doing by contradiction, right? Proof by see this proof you start understanding, you will understand many things later also, right? BCH codes, linear codes, so things will be clear to you, yeah. And why van der Waals matrix will come in the previous class, why we allocated time to it, and everything will come, yeah. Okay, so what is the meaning of that? Okay, minimum distance of D of the code is D and less than C, less than delta, but that is okay. So what do you mean by D of C is equal to D? Okay, that means implies there exist. Yeah, can somebody say there exist C of X belong to C with what? Distance of weight, right? है ना? So distance is D means at least one code word will be there with weight of that. This is equal to D. Am I correct? Yeah. So
sir.
yeah. Let us take let my C of X equal to C naught plus C1 X plus and so on plus some Cn minus 1 X power n minus 1. Cn minus 1 X power n minus 1. Okay. Yeah. So I went up to this extent. And now my weight of Cx is equal to D. It is less than delta. There where we are. Okay. Now, so this means that so there is a support, right? Support means where the coefficients are not equal to 0. Let support of C of X. Okay. Let us call some vectors, right? So I1, I2. So I1 से शुरू करते हैं. So I1 means what? So these coefficients, right? C0 also not equal to 0. Then I1 becomes C0. 0. Sorry, I1 becomes 0. Okay, I'm taking only the, okay, let us I write that way. If you non-zero coefficients, I told it is not better, right? So CI1 I will write. CI1. So CI2. Up to what extent I will go? Can somebody help me? Recall support of Cx is the non-zero coefficients. Now weight equal to the number of non-zero coefficients, right? That is cardinality of Cx, support of Cx, right? So can you tell me where I'll go? CI1, CI2 up to
CID.
CID, right? So luckily CID coming. Yeah, so CID. So CI1, CI2 up to CID, right? So these are the non-zero coefficients here. Okay. But now you know that it is a code word. So what do you know about that? C of X belong to C implies what? You know something? The linear codes. Yeah. So when a word is a code word, right? In place, say something. Some vector is a code word. That means some polynomial is a code polynomial. Then
It's more multiple of
gx. Yeah.
some
So that
GX.
means
Yes.
that g of x divides cx, right? So g of x divides cx means what do you know now? This alpha power a plus 1 and so on. So can you say something about them now?
They are roots of
Are
GX.
roots of they are already roots of gx are roots of cx, right? Good, very beautiful. Okay, so by the way, what is that I want to show? I want to show that the distance is at least delta, but I'm going by contradiction. So when I'm going to prove now, if I able to show that this is a zero polynomial, then what happens? I'm done, right? Okay. So if I show, I'm taking that non-zero code word, okay, prove by contradiction. So non-zero polynomial. If I able to prove that all the coefficients are zero, that means there is no support, then I'm done, right? Are you following? That is a contradiction I'll get. Is it okay? Not okay? Please let me know.
I did not understand what you said.
I'm saying that finally I'll prove that actually C of x is a zero polynomial. Is it give a contradiction or
Okay,
not?
okay,
Right?
okay. Yes, sir. Yes.
That is I want to show. So for that I want to use these are the roots of this polynomial. Okay. So finally I'll prove that. See, I prove by contradiction. Contradiction means what? There is a non-zero polynomial whose weight equal to d and it is less than delta. So but I'll
Yes,
prove
sir.
finally contradiction kaise aayenge. I'm telling in a priori. Contradiction
Yes.
comes,
Okay.
I show that the C of x is the zero polynomial only. Yeah. How do you get it? That where am you going to use these things? That is now cakewalk. Okay. So what do you mean by these are the roots of the polynomial? Right. Now my C
Degree
of
is at least that.
1 minute. How the C of x now look like after having the support? Remaining are zero, na? Remaining are zero, right? Remaining coefficients are zero. Now can you say something that how my C of x look like? So it is C of Ci1 into some x power I1, right? I don't know exactly, but some yeah, this I don't know. Are you following my point?
What is CP1? Okay, that thing. Yeah.
Okay, I'll tell you. Okay, so Ci1 is some number, right? Yeah, so Ci1. So, but for that I need to tell that these are I1 less than I2 less than ID. Okay, so these are greater than or equal to 0, less than n minus 1. Are you following? This is the polynomial. Na? I'm taking
Yes.
d
Yes.
coefficients are
Yes.
non-zero. So I1 can be 0, but I don't know exactly. So now remaining are 0. So can you tell me now what is the resulting polynomial? Ci1 x power I,
Plus
right?
x power I1 plus
Yeah,
CI2 x power I2 and so on.
x power ID. So it is like this, right? I suffix t. So the polynomial is going to be like this, correct? Now what is that I'm doing now? But what I know, C of alpha power a equal to 0. What is the meaning of that? C of alpha power a is equal to 0. So how this equation now becomes, right? So Ci1, yeah, alpha power a power I1, right? Like that. CID, right? Alpha power I1, alpha power a power ID equal to 0. Are you following?
Yes, sir.
Yeah, ID is equal to 0. So can you tell me similarly next one? Ci1 alpha power a plus 1 power I1. I'm substituting, these are the roots, right? Just substituting and I'm going to get CID alpha power a plus 1 power ID. Those who are there in the previous class, for them it is easy. Yeah, so like that we keep on substituting, but in general also easy, nothing is there. What is the last equation? CID, correct? Alpha power, CI1 only. Yeah, sorry, CI1. Yeah, can you tell me what is this?
A plus delta minus 2.
A plus delta minus 2 power I1, right? So and so on plus CID alpha power A plus delta minus 2 power ID is equal to 0. Yeah, right. Okay. So let me save it. So how can you convert into matrix form? Correct? Yeah. How do I convert into matrix form? Correct. So let me write in a new page. Yeah. So you understand that. So we'll get some here. Something will come is equal to 0, right? 0, 0, 0, 0, right? Here what I'm going to get CI1, CI2, and so on, CID. Correct? What is the first row? Yeah, here alpha power AI1. Are you following? Not following.
Yes.
Yeah, it is easy, right? This alpha power A times I1, alpha power A power I2, alpha power A into I2, and so on, alpha power A into ID, right? Yeah. What is the second row? Alpha power A plus 1 into I1, and so on, alpha power A plus 1 into ID, right? What is the last row? Alpha power A plus delta minus 2 into I1, right, up to alpha power A plus delta minus 2 into ID, right? Okay, yeah, good, nice. So when my this becomes zero vector, CI1, CI2, CID becomes zero vector, when? To prove that one, what is that I have to show?
The matrix is invertible.
This matrix is invertible. That means that the determinant is not equal to 0. That is what we done in the previous class, Vandermonde matrix. So I do very simple thing that, so from the first row, what I can take common, or first column, from the first column, what I can take common, do you able to see that? Are you able to see that here, what is common in this first column?
Alpha power AI1.
So I'm taking that, so now, so I'm taking I'm calling some A. What is the size of this matrix? How many rows are there?
D cross
A plus?
delta minus.
No, you are correct. 1 minute. What is that I'm substituting? First I'm substituting alpha power A plus 1. These are how many equations are coming? How many roots I'm substituting, right? So that is number of rows equal to,
Delta
yes,
minus 1.
delta minus 2. Are you okay?
A won't be there, right?
A won't be there. You are correct. You are correct. A won't be there. You are correct. Yeah, you are correct. Wonderful. Yeah. Delta minus 2. Yes. Yeah. Because I'm starting from here. A won't will come. Yeah. So, and but again, you are correct. 0 se shuru karna hai, right? A plus 0, A plus 1, A plus delta minus 2. So, what is that you are saying?
Delta minus 1.
Yeah, you are absolutely correct. Yeah. Yeah. Delta minus 1 cross. How many columns are there? That is support of that D, correct? Yeah, very good, beautiful, right? So this is the size of that matrix. So let us call my D equal to determinant of this A, right? Okay, now this is equal to, as you rightly pointed out, this product, so product I'll take from J is equal to 1 to D. No, why I'm taking up to D? From each column I'm taking, how many columns are there? D columns are there, right? So I'm for each column I can take something common. What is that I take common? A power I, yeah, A power, not this part, sorry, I made a mistake. Yeah, you tell me, that will be better. I know the answer.
We are taking D equal to delta minus 1, right?
See, D equal to delta minus 1. No. See, how many columns are there here?
D.
D columns. First column, what I can take, bring outside.
No, but my question is that we should take D equal to delta minus 1, right?
No, I am not telling that now D is less than delta. That much only I know at this juncture. I am assuming that.
But then we cannot talk about determinant if the matrix is not square matrix.
Okay. You are correct. You are absolutely correct. Very nice, pertinent question you asked me at this juncture. Very much correct. Okay. So what to do now? Yeah, very nice question. So what we do, we'll take the first D equations only. Yeah, you are correct. Thanks for correcting me. I'm making a blunder actually. You are correct. Thanks. Yeah, let me correct it. Thank you. Actually, this is right time पे आपने रुका दिया मुझको. Yes. Now take, since I know that we know that, yeah, good. We know that D is less than or equal to delta minus 1. So collect first D rows only, right? Yeah. Then D is equal to determinant of that. D equal to determinant of A D cross D part. So it is not A. Yeah, I hope you understand. The first D rows of A. Yeah, okay, good, nice. Yeah, now it is equal to, yeah, I'll write below. Yeah, thanks, Amya. This is a very nice observation. Yeah, now tell me. Now the first row I am getting alpha power. Yeah, please. Yeah, somebody can tell me from the first row what I'm getting. Hello, am I audible? Okay. Am I audible or not, please?
Yes, sir.
Yeah. From the first row, what I can get? Take outside.
Alpha power A I1.
Very good. Yeah. So alpha power AI1. Second row.
Alpha power A I2.
Yeah. So like that I can take, right? So I am writing J is equal to 1 to D cross D matrix. Now can you tell me it is alpha power A times
ID.
I J, right?
Yeah, IJ.
J I am taking product, okay?
Yes.
So alpha power AI1, alpha power AI2, like that. So then what is the resulting matrix now left? It is a determinant, right? So first row पे क्या बचा है? You see here, I take AI1, alpha power AI1, I put outside. From second column, alpha power AI2, I बाहर लेकर आया था. Like that, ये alpha power AID बाहर लेकर आया था, है ना? So what is this becomes now? So first row becomes 111. Are you okay? Are you okay or not?
Yes, sir.
What is the second row now becomes?
Alpha power I1, I2.
Oh, very good. Alpha power I2. Thank you. Yeah, alpha power ID. Correct. So like that, can you say the what is the last one? Be
Alpha power
careful.
delta minus 2.
No. But be careful here that I'm not going up to delta minus 2, right? I'm stopping somewhere in the middle because D cross D matrix only I'm going. So I'll tell you, but you can check this later. So it is D minus 1, right? It is easy. 1 to starting. So D minus 1 into I1. So like that alpha power d minus 1 into id. Is it okay?
Yes, sir.
Yeah. So now you know that this is equal to what? So now this is further equal to this determinant equal to product j is equal to 1 to d, right? Alpha power a power ij multiplied with product so k greater than 1. Okay. So alpha power I1 minus alpha power ik minus il. Yeah, I'll write much better. Yeah. So you know that yeah. So I took j here. That's why I'm writing k and l here. Okay. L. You remember this? So Vandermonde matrix by determinant by you get like this. Okay. Just recall that previously. Yeah. So now these are all distinct, right? So this is not equal to 0. Okay. So that means that this implies that my CI1, yeah. So CI2 and so on, CID is equal to 0 vector. We got required contradiction. Is it okay? Why these are distinct? You know that alpha is a primitive. So when k greater than L, ik greater than IL, the alpha ik and alpha IL are different. So the contradiction. Any questions? I hope you like the proof.